everybody. Well, first of all, thanks so much for the invite to this wonderful conference, and congratulations to the organizer for putting this wonderful workshop together. I'm really looking forward, and I'm very honored to be here. My name is Sebastian Will. I have a physics research group at Columbia University in New York City. And I'm going to share some of our results today that we have obtained in microwave shielding and cooling of ultracold dipolar NaCs molecules. And since this is the first talk of this conference, I will give some introduction, not too much, because the time is tight. So, you know, sometimes when people ask me, why are you studying molecules, I give some, fancy answer, about quantum simulation, quantum computation, and whatnot. But in some sense, what truly fascinates me of studying ultracold molecules or molecules in general is that it's in a tradition of obtaining quantum control over ever more complex quantum systems. And in some sense, this is an experimental effort that goes like over the last 100 years concurrently with the theoretical development of quantum mechanics. And whenever we were able, or the community was able, to get quantum control over a new quantum system, it opened new opportunities for science and technology. So in some sense now, molecules seem to be and are a new frontier for quantum control. Well, is it really a new frontier? Well, if you allow, let me share some local patriotism. Maybe I.I. Rabi, one of the faculty at Columbia University in the last century, could be called the father of quantum control. So when he flipped in his apparatus a nuclear spin about 90 years ago, it was probably one of the first times, if not the first time, that a quantum spin was, flipped in a deterministic way by a human. But it's actually interesting to note that the nuclear spin of lithium that he flipped was not a nuclear spin in atomic lithium, but it was actually in a molecular beam machine that used molecules. So from the very start, molecules played an important role. And one may ask oneself, what did we do the last 100 years that quantum control of molecules is still a frontier? Well, it's a frontier because in molecules, we have all kinds of degrees of freedom that need to be controlled to get full quantum control over the molecule, vibrational states, rotational states, and hyperfine states. And we also would like to prepare molecules in particular states. A state that we are particularly interested in is preparing molecules in their low vibrational ground state, because that's the internal ground state where the molecule cannot decay in a single particle process anymore. So it was understood for quite some time that if we are able to quantum control molecules, that it would be possible to study all kinds of interesting physics. Proposals range from studying novel many-body quantum systems, doing quantum simulation of quantum magnetism, doing chemistry with an unprecedented level of quantum control, and using molecules for quantum computing. So there have been many proposals over the last decades. And in these proposals, often dipolar molecules play a particular role. Well, why dipolar molecules? Well, dipolar molecules have dipolar interactions, and dipolar interactions are really interesting. They are long-range in character. They decay following a 1/r cubed law, and they have an angular dependence. So when dipoles meet side by side, they repel each other. If they meet head to tail, they attract each other. And that is an interesting interaction because if it's strong, it should allow one to create strongly interacting many-body quantum states. And it should also be quite effective in creating highly entangled quantum states, which obviously is of interest. Well, dipolar particles are, of course, around in several shapes and forms, not only molecules. So systems that have been studied quite extensively already is magnetic atoms and also Rydberg atoms. It's kind of interesting to compare dipolar molecules in the way that we produce in our lab to these kind of systems. So the main things to highlight is that the effective dipole moment of magnetic atoms is relatively small. And what is great about magnetic atoms is that they are very long-lived. And combining, the combination of these properties allows to study really interesting quantum phases. For Rydberg atoms, we have interactions that are dipolar interactions that are extremely strong. The dipole moment is extremely large. But on the other hand, since Rydberg atoms are in an excited quantum state, they are short-lived. So basically, one mostly has to deal with frozen systems where the particles cannot move during the time the particles are in the Rydberg state. For molecules, they are somewhere in the middle ground. The interactions are somewhere in between magnetic atoms and Rydberg states. And, well, one would hope that one can create molecular systems that are stable and long-lived and should allow to study many body quantum states in the presence of mobility. Well, the door to this field was opened widely by now 15 years ago through the seminal work by Debye and Jinier, creating rubidium-potassium molecules. And since then, the field has made many interesting advances. So this is clearly a completely, incomplete list, a random selection of interesting things that were studied. But from the very start, it was also clear that stability of these quantum systems of dipolar molecules, of ground state molecules, is an issue, or is something that needs to be addressed. It allows, on the one hand, to study chemistry in a new controlled way, but basically it was found that you have universal loss processes that can shorten the lifetime of molecular samples. So over the last 15 years or so, about a dozen groups in the world have realized ground state molecules of bialkali systems, and this is quite some progress. But despite all progress, challenges that have remained are that the gases that have been created are relatively hot, and there are fast losses when the molecules collide, and that has in some sense also inhibited progress. So this situation changed over the last few years by developing and demonstrating methods that actually shield molecules from undergoing lossy collisions. And one method to highlight is the resonance shielding using static DC electric fields that was realized in Junier's lab, and microwave shielding of NaK molecules that was realized in Xinyu's lab in Munich. And in both cases, it was shown that you can dramatically reduce the loss rate in these molecular samples. But in both cases, it was actually fermionic molecules, and fermionic molecules sort of intrinsically are already a little bit more stable than bosonic molecules because you have a p-wave barrier, and the tunneling through the p-wave barrier already slows down loss processes by a bit. So an interesting question to ask is, what about bosonic molecules? How do bosonic molecules do? Or is shielding possible in bosonic molecules? And well, in my lab, we pick a bosonic molecule, Sodium-cesium, and the main motivation to pick it initially was actually that it has a very large dipole moment among the chemically stable bialkali molecules. It's the largest dipole moment of 4.6 dBi in the ground state, and that's in a more visual number. That means that at this dipole moment, you should have an effective range of dipolar interactions on the order of tens of micrometers. So typical interparticle spacings in molecular samples in micrometer. So here you have an interaction range that's a lot longer than that you should be able to achieve. And you can tune this with external electromagnetic fields. So let me first tell you a bit how we synthesize our sodium-cesium ground state molecules. So there has been a whole series of works over the last 2 years where we have described how we do this and what we can do with this. And I'll go through that. So our effort started actually 5 years ago, a little bit more than 5 years ago in an empty lab at Columbia University. By now it's a little bit more busy. So that's the laser table for laser cooling of sodium and cesium atoms. The right side is sodium, obviously, with the orange characteristic orange light. The cesium has infrared light, so you don't see it. That light is transferred to a second optical table with a vacuum chamber on it, and then you can zoom into this vacuum chamber. And the first step that we do there is create Bose-Einstein condensate of sodium. We can reach up to 5 billion atoms. We do this in a quadrupole trap that is optically plugged with a green laser beam, and then the atoms are transferred to a cross-dipole trap to achieve Bose-Einstein condensation. Then it turns out, and I spare you the details, but the nice news is, and that was inspired by work done by Simon Cornish, who showed that you can actually cool rubidium and cesium sympathetically in a quadrupole trap. So we also thought like, well, we don't know much about the scattering properties of sodium and cesium, but let's just throw them together into the quadrupole trap and see if they can be cooled together. And lo and behold, this actually works, and we can make dual NaCs of sodium and cesium with quite healthy numbers. And it turns out that in our 1064 nanometer optical dipole trap, the differential gravitational sag between the species is almost zero, so just like 1 or 2 micrometers. So the clouds are really overlapped. So we have a nice system of overlapping NaCs, overlapping superfluids, which would be actually interesting to study in its own right. But of course, we just plowed on. We plowed on to synthesize sodium-cesium Feshbach molecules. And well, it turns out, everybody who has worked with cesium before knows that it's not a trivial atom to work with. So we need to prepare our sodium-cesium sample at a magnetic field of around 890 Gauss. And it turns out that the Feshbach resonance, the sodium-cesium interspecies Feshbach resonance that we need to associate molecules at 864 Gauss. So thank God it's not too far away from the working point where we prepare the mixture, but it's all at a fairly high field that we need fast control. And while we are going to this Feshbach resonance, the scattering length of cesium becomes pretty bad. But it turns out if we ramp quickly enough, things are actually very controlled. We can make samples of about 50,000 sodium-cesium Feshbach molecules, which is a great sample size. And now we have created molecules essentially in the highest vibrational state of the molecular potential. And the next step is that we want to go to the absolute low vibrational ground state. Well, that we do with a 2-photon approach that I'm sure many of you know about, the Stirrup scheme, where we coherently link the Feshbach state to the absolute ground state. Here just an impression of the laser system. And we can do this Stirrup transfer. Here, this was data that we published earlier this year. But actually, by now, we have been able to improve the Stirrup efficiency to about 90% one-way efficiency. So we can make about 40,000 ground state molecules at densities above 10 to the 12 per cubic centimeter, which means interparticle spacing is a little bit closer than a micrometer. Okay, now we have our samples of 10,000s of sodium-cesium molecules in exactly the same internal quantum state. So that is now a perfectly initialized sample that we can, exercise quantum control upon. So let's get started with this. We started working on microwave control of sodium-cesium. Well, and initially we prepare our molecules in the rotational ground state, J equals 0, Mj equals 0, and then we can drive microwave transition to the first rotationally excited state. One thing to note is we do this at our high magnetic field of 864 Gauss. So it turns out that nuclear spin is basically split off from the rotational quantum number. So really this picture that I draw here is quite accurate. We're kind of in the Paschen-Bach regime. And we can now drive the 3 transitions that are allowed. And this is done here. So we take a rotational spectrum. One curiosity to note is the spacings between states is just a few kilohertz, extremely close to space. So to actually have more control over how to address these closely spaced states, we built a new antenna in our setup that allows us to create very clean, circularly polarized microwave radiation. And just a few years ago, somebody asked me about it, and I would have said, like, well, that's near impossible, in this like messy environment with this field chamber and all that, that's very hard. But we developed this design here, a planar design with 4 loops that can be phase controlled with respect to each other. And the whole antenna is like 0.5 millimeter thick. This is a 3D printed mount. And actually, It's integrated then in our vacuum to the, our vacuum chamber on the outside of the viewport, and we reach here an electricity of our, circularly polarized microwave field of like 2 degrees roughly. So it's very high purity. And well, we intend it for microwave control on our molecules, but perhaps this design is also useful for other applications where you care about very clean polarization microwaves. Okay, so we apply this to our molecular sample, and well, we found actually the first surprise. We select sigma minus polarization in this antenna, and what we find is that we achieve a Rabi frequency of above 40 megahertz. It's extremely fast control on the rotational state, and we also do this with sigma plus. We get a similarly high Rabi frequency. So if you interpret this in a quantum information kind of context, it means that we can do pi over 2 pulse in 6 nanoseconds. That's actually quite amazing. If you compare to other quantum information systems, even superconducting qubits, the control times are not faster than that. So it's quite cool. But again, right now we are not interested in quantum computing with molecules in this setup, so we move on. Yeah. That's a clean polarization. Okay. That's right. So we move on to microwave shielding of sodium-cesium molecules. And actually, the timing couldn't be more perfect. This paper just came out today. Pure coincidence. Well, microwave shielding. Well, we now take our sigma plus polarized microwave field and detune it to the blue. And as was proposed in several theoretical works and also shown in earlier experiments using calcium fluoride molecules in a tweezer, and also the sodium-potassium results from Munich that I mentioned earlier, it is possible to actually effectively create a repulsion between the molecules. Basically, you set the molecules in rotation, and no matter how the molecules approach, they repel each other, because they reorient each other as they approach each other to always repel. So we can write this down as like a energy versus intermolecular distance collisional potential. And if we prepare our molecules in the plus stressed state using the microwave field by adiabatically ramping it on, we actually get a scattering potential that has here a strong repulsive barrier. This is what we want. So pairs of molecules don't reach short range where they get lost to sticky collisions or whatever the process is. I should say, if you blow up here this energy scale, you actually see that there's a attractive potential here. So that's actually something you should keep in mind. It's going to become important. Well, so let's do microwave shielding. Well, let's first get the baseline. What kind of sample lifetime do we have in sodium-cesium if you don't microwave shield? Well, here you see it. I point out this is a log-log plot, so so just you note that orders of magnitude on the x-axis. So initially, the 1/e lifetime is like 10 milliseconds or so. So very short sample lifetime at a density of 10 to the 12 per cubic centimeter. Okay, now let's switch on shielding. We apply our antenna with sigma plus radiation. We actually see an extension of the sample lifetime by almost a factor of 100. So now we have a sample lifetime of a second. That's getting into the range of normal ultracold gases. So that's very, very exciting. So that is when we do things under optimal conditions. So let's actually scan a bit the parameters of the microwave field. What I plot here is inelastic rate coefficient versus detuning of the microwave field over Rabi frequency, which is what we often call the shielding parameter. And if shielding is very far detuned, if the microwave field is far detuned, you expect to get the loss rate of the unshielded gas. So we get this here. And then we reduce the detuning of shielding, and you see how the loss rate goes down. And you also see the shaded area. That's the theory curve produced by Thijs Carmen. So we get a very nice following of the theory curve there. And get here a minimum of the two-body loss that is more than 200 times suppressed over the unshielded case. So that's very cool. Well, you see already something goes up here for small detunings. Well, oh, actually, one thing to point out. So while we are changing the detuning of the microwave field, we are also changing the effective dipole moment of the molecules, because the smaller the detuning, the more and more we admix the rotationally excited state into the dress state. And by this, we increase the dipole moment of our molecule, which actually is the reason why the shielding becomes more effective. Okay, but at some point here, the shielding isn't effective anymore, and our data goes up. We measured also the data for a different temperature, and interestingly, at a lower temperature, things get worse. Kind of counterintuitive. So what could it be? Well, one obvious guess is, well, it could be some beyond two-body physics that's not captured by the C rule. C rule is just including the two-body processes. So maybe three-body, something like that. Okay, so hold that thought. We'll come back to the question later. So for now, we are enjoying our 200 times suppression here, and continue also studying the elastic scattering under shielding. And for that, we do a cross-thermalization experiment. We switch off shielding for a short time, the cloud heats up, and then we switch shielding on again, and you get a rethermalization. Doing that, we can measure the thermalization rate experimentally. And in discussions with Thijs, it actually turned out, well, we need to be careful of how the thermalization rate relates to the elastic collision rate, which is what matters when we want to extract the elastic scattering cross-section. And it turns out that actually, as a function of the shielding parameter, the number of collisions you need to thermalize increases dramatically from the unshielded case. So when dipoles come into play, you have mostly forward scattering. So you need actually more collisions to thermalize in the perpendicular direction. So that is something to note. That was important to actually understand what we observe here. There's also another interesting thing to note is, as we go to smaller detunings, the dipolar range in the system increases, which actually means that our scattering process, crosses over from a quantum description to a more classical description, where actually temperature plays a role. So to get this right, you actually also need to take into account the temperature. All right. So with both the inelastic and the elastic data obtained, we can calculate the ratio of elastic collisions to inelastic collisions. And we actually, which is a figure of merit that's important when you think about evaporative cooling. And we obtain here a number of up to 4,000. And as we kind of realized in our work, in our paper, well, you kind of need to also divide to be faithful by this number of collisions that you need to thermalize. So maybe the more faithful figure of merit is gamma over n col, which is about 250. Still a good number. You should be able to evaporate our gas. So, well, that's exactly what we do. Here you see phase-space density versus molecule number. We start with several 10,000s of molecules at a temperature of 750 nanokelvin. And then we reduce the dipole trap depth in a ramp that takes about 1.5 seconds. And we can cool the gas from 750 nanokelvin to about 30 nanokelvin and increase the phase-space density to about 0.1. So we get about a 20 times increase in phase-space density and an evaporation efficiency on the order of 1. And it's actually noteworthy, this is the first time a bosonic molecular gas in the ground state. So that's cool. And it begs the question, can we cool further to BC? And well, for that, we need to solve our issue at small detunings of the shielding parameter. So let's try to get some insight on what's going on there. Well, what happens at small detunings? Well, I pointed out before that our scattering potential has a little attractive dent. And for large detuning, it may be this blue line. For a smaller detuning, it's maybe this red line. And as we know from early visionary theoretical work and the recent experimental work also by the Munich group, there are filtering bound states. There are bound states in this collisional potential. But it's still remarkable. This collisional potential is really exotic. The barrier is at thousands of Bohr radii. The well depth is just a few tens of kilohertz typically. And the binding energy of the bound state is like a kilohertz or so. But yeah, you can map out also theoretically. So we collaborate for that with Chris Green, figure out where the bound states are. And well, an obvious process that may be happening here is if you have the bound state, you can have recombination with that bound state. Well, let's see first if you can really distinguish 2 and 3 body loss very precisely. And for that, we measure time series of the molecule number versus hold time for different shielding parameters. Here for large detuning, we see that we can only fit the data very well by a 2-body fit. And for small detuning, it's quite clearly a 3-body loss. So we really established that we have a 3-body process here when the detuning is small. And we did that for all kinds of different shielding parameters. And we observe here how we cross over from a 2-body loss process to a 3-body loss process at small detunings. And the presence of the bound state coincides with the observation of 3-body loss. It's a quite strong indication that this recombination process is. Okay, so this really opens up a prospect for dipolar molecular gas, ultra-cold gases. I think we are now at a place where one can regard it as a new modality for quantum simulation. I want to point out that one really cool thing about microwave shielding is that you can quasi-instantaneously change the scattering properties. Microwave can be controlled on a nanosecond scale. You can change the detuning really quick. You can go from a gas that has a very small interaction range to a gas that has interaction range that is larger than the interparticle spacing. So that gives interesting opportunities for non-equilibrium physics. Perhaps also new field K-type approaches of tuning interactions. There are exciting prospects to create interesting phases of dipolar bosons in 3D. This was very nicely presented in this paper. And also in this paper, it was pointed out that you want to have independent tuning of dipolar interactions and S-phase scattering lengths. Interesting phases in 2D systems. And here also NaCs should be an interaction range where you could reach interesting phases. And of course, also loading the molecules into a 2D lattice and observing it with a quantum gas microscope should be quite aided by the shielding that should help us to get a high filling fraction in these systems. Okay, very briefly, there is a little bit more on molecules at my lab. We actually have thought about laser cooling schemes for real-world molecules. For example, the carbon dimer. You find all the details in this paper. Also, my student Nicolo Bigali is here, who you can talk to about this, and he can tell you everything about it. We kind of extended this approach to OH plus molecule, and interesting to note is that both these molecules do not have a diagonal quantum factor, and still it seems they can be laser cooled. So perhaps this is an interesting idea that leads to a rethinking of that maybe a broader class of molecules could be laser cooled. And that's a question that we actually started to analyze in collaboration with your very own, now actually New Yorker, Anna David. And she will give a talk later today about this effort. And I will skip the brief overview of what we do with strontium in optical tweezer arrays. And we'll just summarize that we have created a near-degenerate molecular gas of sodium-cesium. I believe from what we see, we have really been blown away of what you can do with microwave shielding over the last one and a half years. This is really likely to become a workhorse technique in the field. In some sense, I think we're just at the beginning. So with that, I want to thank my group. I want to point out the fantastic work of my postdoc, Ian Stevenson. So he's on the job market later this year. So if you are interested in hiring someone who knows everything about ultracold molecules in the lab, and you should watch out for him. And I want to highlight also Niccolo Bigali, who is here in the audience, a senior graduate student in the lab, Claire Warner, who has contributed important work on this, Silwei Chang and Wei Jin Yuan, and Emily Bellingham, the younger graduate students. And if you're interested in joining, let me know. For interested postdocs, there's actually a fellowship that I want to announce, and you need to be very spontaneous. The application deadline is September 13th, so talk to me immediately if you're interested. And with that, thanks so much to all our collaborators here at POC and Poster Advertise. Thanks to the funding agency, and thank you all for your attention. Thank you very much for today's talk. Now you have some time, please. Yeah, so working out the details of the temperature dependence is actually still an open question. We're talking to Chris about that. But what is kind of noteworthy is that if it was, a process that would be just tied to tunneling through the barrier or a non-adiabatic transfer to an unshielded state, it should be something that actually gets less significant for colder temperatures. So the fact that it goes up for higher temperature, for lower temperature, is kind of indicating that there's something beyond the two-body potential. But how the precise scaling is an open question. Please. Great.
In this recombination process, there's only very little energy released, right? Because the molecules are very weakly bound to stepulars. Yeah. So we should be able to detect them.
Yeah. So basically, it depends a bit on the regime that you work, but it can be several kilohertz. And note that we can make these measurements at temperatures on the order of 100 nanokelvin. So that is actually 2 kilohertz in terms of frequency. So even a binding energy increase of just a few kilohertz, we are sensitive to, or energy released on that point. We should follow this.
Took a while, sorry. So in your paper, there was also a discussion of the elastic aspect scattering length, which seemed a bit mysterious at the time. So are there any new insights about that from these measurements?
Yeah, we basically fit it from the experimental data for the long range. And I don't think there are new insights on why it's deviating from what you expect theoretically, but we can discuss with them guys later.
Okay, another question? If not, we can find once more. Sebastian?
Okay.